we will see energy band splitting. How the energy band diagram has been created. For that, this concept is required, that is energy band splitting. So, we are going to deal with the semiconductors only. Semiconductors like silicon or germanium. So, when you take silicon, its atomic number is 14. Atomic number is 14. So, if you know this information, you can able to tell certain things regarding the silicon atom. One silicon atom I am talking. Okay. So, if you take one silicon atom, it is having the atomic number is 14. So, that I can tell 14 electrons are available, 14 protons are available, and protons, neutrons are available in the nucleus, and these 14 electrons are revolving around the nucleus in different orbits. Okay. And about those different orbits, we can give the information using the electronic configuration of this one silicon atom. What is the electronic configuration of one silicon atom? 1s2, 2s2, 2p6, 3s2, 3p2. This is the electronic configuration of one silicon atom. What is the information we are getting here? This 2 is representing 2 electrons, this 2 is representing 2 electrons, this 6 is representing 6 electrons, this 2 is representing 2 electrons, this 2 is representing 2 electrons. Totally how many electrons are there? 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 2 is 14 electrons are completed. But all these 14 electrons are not available in the single orbit. That means if it is a silicon nucleus, then in only one orbit, all these 14 electrons are not available. It is representing the first orbit. First orbit. This one is representing the first orbit. This 2 is representing the second orbit. Second orbit. This 3 is representing the third orbit. So, in the first orbit, how many electrons are involved? 2 electrons are involved. In the second orbit, how many electrons are involved? 2 plus 6, 8 electrons are involved. In the third orbit, how many electrons are involved? 2 plus 2, 4 electrons are involved. So, around the silicon atom, there is not a single orbit where all these 14 electrons are involved. There are 3 orbits are there. So, I am taking this is the first orbit, this is the second orbit, and this is the third orbit. In the first orbit, we have 2 electrons. In the second orbit, we have 8 electrons. So, 1, 2, this is 4, 5, 6, 7, 8. Okay, in the second orbit, I have indicated 8 electrons. In the third orbit, we have to indicate 4 electrons. So, 1, 2, 3, 4. So, this third orbit is important for us. Third orbit. This third orbit can also be called as valency orbit. This third orbit can also be called as outermost orbit. Even though the one silicon atom is having 14 electrons, all these 14 electrons are not responsible for the production of the current. What is the reason for that? Means the nucleus is of positive charge because of the presence of the protons and electrons are negative charge. So, out of 14 electrons, 10 electrons are involving in the first orbit and in the second orbit. All these 10 electrons which are available in the first 2 orbits are highly attracted by the nucleus. So, we cannot able to make those 10 electrons available in the first 2 orbits free. But the electrons which are available in the outermost orbit can be made free by providing the external energy. That external energy can be provided by using the temperature, or external energy can also be provided by using the voltage, that means electrical supply. So, by using this particular supplies or optical energy also we can able to take for the energizing the outermost electrons. By using this thermal energy, electrical energy or the optical energy, we can able to energize the electrons which are available in the outermost orbit. So whatever the current we are getting from this particular silicon, that current is due to those 4 electrons only. The electrons which are available in the outermost orbit only, or in the valency orbit only. Okay. The electrons which are available in the valency orbit are called valency electrons. Valency electrons, only these valency electrons are responsible for the production of the current. Not all the 14. Only the 4 which are available in the third orbit or the outermost orbit are responsible for the production of the current. This is about one silicon atom. Okay. Now, actually our topic is about energy band splitting. So, when you have one silicon atom, we have understood that 4 electrons are responsible for the production of the current, not all the 14 electrons. Now, when you take n silicon atoms in the silicon material, n silicon atoms are there. Then how many valence electrons will be there? One silicon atom is providing 4 electrons. Like that, n silicon atoms are providing 4n electrons. 4n valency electrons. Otherwise, for more clarity, I am writing here valency electrons. Here also valency electrons. But when you observe one single silicon atom, we have understood that the electronic configuration is given by 1s2, 2s2, 2p6 and 3s2, 3p2. The third orbit is involving 2 electrons in one level, and the same third orbit is involving the 2 electrons in the another level. Okay. So, this is what we have observed in the one silicon atom. Now, when you take n silicon atoms, then actually these are total number of electrons from the third orbit is 4 electrons only. And here for the n silicon atoms, the total number of electrons, valence electrons will be 4n electrons. So, in the 3s level, how many electrons will be there? In the 3p level, how many electrons will be there? One silicon atom is involving 2 electrons in the 3s and 2 electrons in the 3p. Total n silicon atoms are involving 2n electrons in the 3s levels and 2n electrons in the 3p levels. Okay. So, this is what we can able to understand. So, when you take the diagram in such a way that on the y-axis I am taking energy, carefully you see here I am not writing the units of the energy like joules. I am writing the units of the energy electron volts. And on the x-axis what we need to take means interatomic distance. Interatomic distance. So, what is the meaning of this one? The distance between two adjacent atoms. When this particular distance is very large, that means on this axis you are at far away. That means the distance is very large in between the any two successive these atoms. Then you will get this 3s level, this 3p level like this for the n silicon atoms. So, 3s level, 3p level. But when you bring all these atoms are very close to each other, that means you are reducing the interatomic spacing or the interatomic distance. When you reduce, that means you are going towards the origin. So, we are drawing the diagram from right side to left side. When you are here, the interatomic distance is large. When you make the interatomic distance is very close, then what will happen? Very close in the sense you are going to origin. At that particular time, according to Pauli's exclusive principle, according to Pauli's exclusive principle, what will happen means one energy level should not contain more than one electron. That means each electron should have its own energy. So that in this particular 3s level, how many electrons are there actually? 2n electrons are there. And in this 3p level, how many electrons are there? 2n electrons are there. So, this particular 3s level will be splitted into 2n energy levels. Okay. And this 3p level will also be splitted into 2n energy levels. On y-axis, we have taken energy. That means these will be energy levels, different energy levels we have taken. When you are here, certain energy will be there like 1. Examples I am giving. And this is higher than this one. It may be 2, it may be 3, it may be 4, it may be 5, it may be 10. Like this, these energy levels are distributed. So, this is possible. This splitting of the energy levels is done when you decrease the interatomic distance only. When the interatomic distance is very large, there is no splitting of the energy bands or splitting of the energy levels. So, this band we can able to treat. One more diagram I am going to draw now. So, here on x-axis I am taking interatomic distance, and on y-axis I am taking energy in electron volts. So here it has been split like this. Okay. Now further we can able to draw like this. On y-axis same energy. Now this is one band, this is another band. In between these two some forbidden band is there. Like this I can take. All the valency electrons are available here at a temperature 0 degrees Kelvin. That means you did not apply any external energy. We will talk the external energy in terms of the temperature. Okay. So instead of talking in terms of the electrical or in the optical energy, we will talk with respect to thermal energy, that is temperature. When you don't apply any temperature, like T is equal to 0 degrees Kelvin is available, all the foreign electrons are available in the valency orbit only. That means that the valency orbit only we are showing like a here group of energy levels. Yes, I need to tell about energy level. Clearly you need to understand about the energy level. So energy level, for example, E1 is the energy level. Energy level E1 contains electron E1. This is electron E1. This is energy level E1. Then we can tell electron E1 contains the energy. How much amount of energy it has means E1 energy. Energy level we are indicating with E1 and electron is also having the energy E1 on. Okay. So in this particular energy level, if you take energy levels like this, we will take. So this is energy in electron volts. This is one of the energy level indicated with E1. If you know that electron is available in this energy level, then you can tell what is the energy of the electron means E1. Once again I am repeating, all these are energy levels. In the energy level E1, if you have the electron E1, then you can able to tell electron E1 has the energy E1. Now in a different manner I will give in a reverse manner, that is, you know that electron 2 has energy E2. Then this is the information known to you, then you can tell electron E2 is in energy level E2. Energy or energy level both are indicated with E1 and E2 or E3 up to so on. Okay. So in the first case, you know that electron is available in the energy level E1, so that electron can have the energy E1. In the second way, I am telling electron is having the energy of E2. That means where is this energy, where is this electron is nothing but it is available in the energy level which is equal to E2. For example, this is E2. Now the electron will be available in this particular energy level E2. Okay, you need to understand this one very carefully. Okay, now coming to again this particular case, here n silicon atoms you have taken, so that 4 n valency electrons are possible. All those 4 valency electrons are available in the valency band. This is called group of energy levels. Group of energy levels. So all these are 4n. 4n energy levels are available here. So electrons are available. One electron is here, another electron is here, another electron is here. In one energy level, only one electron can be possible according to Pauli's exclusive principle. No two electrons can have the same amount of energy, is nothing but this one only. Okay. So here electrons are available in different energy levels like this. Now, when you increase the temperature up to 300 degrees Kelvin, or you have tried to increase the temperature from 0 degrees Kelvin, then what will happen? The electrons which are available in the valency band or lower band, these can excite and go into the conduction band. This is called conduction band. Okay. So, like this, all these electrons can able to send to conduction band. These are called, when the electrons are available in the conduction band, these are called free electrons. When the electrons are available in the valency band, these are called bounded electrons. This terminology is important for us. Okay. Now, I am going to take this one separately like this. This is interatomic distance, and on y-axis I am taking energy in electron volts. So, this is valency band, and here another band is there, that is conduction band. Okay. So here band is nothing but group of energy levels only. Here so many energy levels are there. And here also same number of energy levels will be available, because when you excite all the electrons which are available in the 4n energy level, so all these 4n electrons will go to the upper level, that is called conduction band. So here how many energy levels are there? Same number of electrons should occupy here also. That means same number of energy levels should occupy here also. So we can tell these are 4n levels. These are also 4n levels. But one thing you have to understand here, this valency band is the group of energy levels. This conduction band is also group of energy levels. And in between these two, some gap is there. This is called energy gap. Energy gap. But in this gap, you will not find any electron. That's why it can also be called as forbidden energy gap. Forbidden means not allowed. So no electron can able to available from this level to this level. From upper end of the valence band to lower end of the conduction band, no electron is allowed. That is why it is called forbidden energy gap. And what is the topmost energy level of the valency band is nothing but that is indicated with EV. EV is the highest energy level available in the valency band. Similarly, the lowest energy level available in the conduction band is EC. So we are going to deal with EV and EC. EV is topmost energy level in valency band, and EC is lowest energy level in conduction band. Okay, and what is the gap which is available in between these two? Means we can able to give in terms of EC and EV. So this gap I am representing with the EG, energy gap. Okay, it is given by EC minus EV. Okay, lower energy level of the conduction band minus upper energy level of the valency band. So this is called energy gap. EG is equal to EC minus EV. And what are the units of EG? Everything is energy only. It is one of the energy level of the conduction band, that is a lower energy level, and it is upper energy level of the valency band. And these two are subtracted, so that resultant is also energy only. That is called the energy gap EG. So it is in electron volts, it is in electron volts minus electron volts will give electron volts only. So this is what we need to understand. Okay, this is about energy level splitting or the energy band diagram, how the energy band diagram has been created. This is the energy band diagram we can able to tell. Okay, so valency band, conduction band, forbidden band, like this energy bands will be available. Okay, then if you take one silicon atom, as we know, nucleus is there, around this one 3 orbits are there, like this. We are interested only in the outermost orbit, so I am drawing the 4 electrons in the outermost orbit. Okay, so 4 electrons are revolving in the outermost orbit of the silicon. This is the valency orbit related to valency band. So 1, 2, 3, 4, like this I have taken, like E1, E2, E3, E4. This is related to valency electrons, valency orbit. The electrons are available in the valency orbit. When you provide the external energy, then all these electrons will go to conduction band. Okay, this is what you need to understand. So this is about valency orbit of this particular diagram. Okay, only this one we are showing like a valency band. So these two orbits are available here. For example, this is the first orbit, this is second orbit, this is third orbit. This is your third orbit. Okay, so this is second orbit. This is first orbit. Okay, here nucleus is available. So in this way we can able to understand how the energy band diagram will be there. With the y-axis is energy measured in electron volts. It is EC, it is EV. Like this we can able to indicate. Then if you go for germanium, its atomic number is 32. So total number of electrons available in one germanium atom is 32. But if you write the electronic configuration, surprisingly you can able to check here 4 valency electrons are there in the silicon. Here also 4 valency electrons will be available in one germanium atom. That's why these two are coming under fourth group elements. Even though many number of electrons are available in this germanium compared to silicon, germanium is also having the 4 valency electrons only. Remaining 28 electrons are the inner orbit electrons only. Outermost electrons are only 4. Here also outermost electrons are only 4. That's why these two are coming under the fourth group. Okay. These two are semiconductor materials.